Hello guys, in this video I will implement the graph transformer structure proposed by Vijay and Xavier. This paper was published in 2021. First, let's review the concept of attention in transformer, which is a very successful model in language processing. The traditional attention in transformer architecture consists of three components: query, key, and value. You can view query as questions to be asked. Key means the keys to your questions, and value means the answers to the questions. For example, you can ask the query, what is attention? To seek answer for this query, you will open your keybook and look through the headlines like what is attention in transformer, what is attention in graph, what is MLP, and so on. Value means the content inside each of these headlines or each of these keys. For each query, you need to scan through all the keys, take the one that is most suitable, and look at its value. So for each query, we need to check against all keys. This concept can be summarized into two steps. In the first step, we compute the attention coefficients between the query and the key. So this is the softmax of inner product of query and key, and here we divide by square root of the dimensionality of query and also the key. Once we obtain the attention coefficients, we simply make a linear combination between this coefficient and the value to get the output. So this is the traditional attention mechanisms. This mechanism works well in language processing because for language, the input sequence is often short. A sentence is often have length maybe maximum 1-200. On the other hand, on structures like social networks where we have a lot of data points and we have to check, we have to compute the attention between any two data points, that would make the complexity big O(n) square, where n is the number of data points. That is quite large and not practical. So I will discuss the concept of sparse attention, which is applied to graph. In graph, we have nodes and we have edge, which indicate where the two nodes are connected. So to compute the attention, we only compute the attention between two nodes that are connected. And here is the structure of the graph transformers. So first we have HI here, which are the hidden representation of the original data points. So basically from original data point, we perform some linear transformation to them and get some hidden representations. This hidden representation together with the positional encoding, which is denoted by lambda. So in this paper, they use Laplacian positional encoding, which I will explain later. Together with the positional encoding, they form the input to our model. So the hidden representation H here will be fed through linear layers to compute query, key, and value. The attention in this layer will only compute the query and the key that correspond to nodes which are connected. And after this, we get an output which can be used for the particular task. Let me make it more precise down here. So our input for the model will be the hidden representation of the node features of the graph and the adjacency matrix A. First, we will project the input, which is the hidden representation, into query, key, and value. And here I assume they all have dimension n and hidden dimensions. Second, we will reshape QKV according to number of hits. In our implementation, we implement multi-hit attentions. So here, assume hidden dimension is equal to the dimension of each individual hit times the number of hits. So by reshaping QKV, the new query key and value will have dimensions n, dh, and h. And the third step is the sparse attention, where the attention here is a function of qk and the adjacency matrix. This is equal to the softmax of qk transpose times a, where this star here means pointwise multiplication, and we scale by the dimensionality of the key and also the query. Basically, the matrix A here control the attention to be computed. For example, we only compute qi kj transpose if and only if aij is equal to 1. That means I and j are connected, or j is in the neighbor of I. So here ni means the set of all the neighbors of I. On the other hand, if I and j are not connected, that means aij equal to 0, then the ij element that come out of this computation will be qi kj transpose times 0. So we don't need to worry to care about qi kj transpose because we times 0. So the resulting matrix in this case will be a sparse matrix because A is a sparse matrix. So note that it's just some technical details here. So this for the time being you don't need to worry about. After we compute the attention, which gives us the attention coefficient here, we combine with the value v to get the output. So we simply multiply the attention coefficient by the value v. The fifth step here is optional. So we will reshape the output into hidden dimensions and then project it. Now I will next I will implement the sparse attention module. Let me put out the model architecture here so that it's easier for us to refer to. I will call this so here we have sparse attentions. So we sorry you guys, so n dot module, we will, in this case we need hidden dimensions and number of hits, let's say here equal to 8. Hidden dimension, we set the default value to 80. Super init. We initiate the hidden dimension to be hidden dimensions, self dot number num hits to be num hit. Right, so next we will prepare the linear layers for query key and values. Self dot q equal to maybe linear q equal nn dot linear hidden dimension to hidden dimensions. Note that our input here are the hidden representation of the original data points which have dimensionality hidden dimensions. And the same way we have linear k and then dot linear I will just make a copy for the value. And lastly, we have projections of the output, which is the OLH in this figure here. So output projection is another linear layer. Next, we will see how the information is flown through this diagram. So here, the input for the forward function will be the adjacency matrix A. A here has shape n by n, which is the adjacency matrix of the graph. H here is a hidden representation of the graph, so the shape is n hidden dimension. First, we will take n equal to the length of h, and h here will be number of head. The head means the hidden dimensions divided by the number of heads. So the first step in this diagram is to put the hidden representation of the data point through the query, key, and value. So I have compute query key value q self h, and here we want to reshape it based on the number of heads for faster computations. For k and v, we will do the same thing. So key and value, we do the same things. Alright, this need to be h. After we get query, key, and value, we will do the sparse attentions. The sparse attention is computed by the following formula here. Why we call this sparse attention? Because here we have position-wise multiplication, and our adjacency matrix A is a sparse matrix. For fast computation of sparse attention, I would use an API, compute attentions scores by sparse matrix API. Let me explain the code for this API. So the code is dglp bstdmm ax1 x2 that compute x1 times x2 and pointwise multiplication with A, where x1 and x2 are dense matrix and A is a sparse matrix. And note that in this case, the pointwise multiplication is applied along the last dimensions or the head dimensions. Pointwise multiplications is applied on the last dimensions. So here we can simply have attention coefficients. Well, I will just use a succession here. QK transpose 1, 0. Why we transpose the first dimensions? Well, here note that A has size n by n, and Q has size n dh and h, K has size n dh and h. So if we transpose the first two dimensions of K, we have dh times nh. So QK transpose, we have dimension n and h. and that match the requirement of this API. This is QK transpose. Once we get the attention coefficients, we can apply the value V or multiply this coefficient by V to get the output. Again, here I would use the API for computing sparse multiplication with sparse matrix. DGL sp.bspmm. We want to multiply the attention score, attention coefficients in this case, and the value V. Well, note that V are shaped N, DH, and H. So when you multiply these two with attention score having the shape N, and H, you will have the output with shape N, DH, and H. And now we will concatenate the H and reproject. So out, we reshape out N minus 1. So in this case, it has N hidden dimensions, and we will project it using our projections, output projection, which is OLH here, and we get the output before we compute the next layer. So this module is the sparse attentions. Right? Well, sparse attention. Okay, I have an import an N. .NN. The sparse attention is computed by the following formula here. Why we call this sparse attention? Because here we have position-wise multiplication, and our adjacency matrix A is a sparse matrix. For fast computation of sparse attention, I would use an API, compute attentions scores by sparse matrix API. Let me explain the code for this API. So the code is DGLP bstdmm ax1 x2 that compute x1 times x2 and pointwise multiplication with A, where x1 and x2 are dense matrix and A is a sparse matrix. And note that in this case, the pointwise multiplication is applied along the last dimensions or the head dimensions. Pointwise multiplications is applied on the last dimensions. So here we can simply have attention coefficients. Well, I will just use a succession here. QK transpose 1, 0. Why we transpose the first dimensions? Well, here note that A has size n by n, and Q has size n dh and h. K has size n dh and h. So if we transpose the first two dimensions of K, we have dh times nh. So QK transpose we have dimension n and h, and that match the requirement of this API. This is QK transpose. Once we get the attention coefficients, we can apply the value v or multiply this coefficient by v to get the output. Again, here I would use the API for computing sparse multiplication with sparse matrix. DGL sp.bspmm. We want to multiply the attention score, attention coefficients in this case, and the value v. Well, note that v are shaped n, dh, and h. So when you multiply these two with attention score having the shape n, and h, you will have the output with shape n, dh, and h. And now we will concatenate the h and reproject. So out, we'll reshape out n minus 1. So in this case, it has n hidden dimensions, and we will project it using our projections, output projection, which is OLH here, and we get the output before we compute the next layer. So this module is the sparse attentions, right? Well, sparse attention. Okay, I have an import an n. N as n. Right. So next we will implement the graph transformer layer, one single graph transformer layer. So note that in this structure we may have multiple layers, L layers. Here, you might look at this picture on the left, or you might look here. There are L layers, and first we will implement one layer and then stack them together. So in this layer, the sparse attention module just now give us the output at this point, and it remains for us to implement the forward pass here to get the output of this single layer. Class GT layer. Well, I already have some suggestion here to save times. So I need to also init attention by sparse multi-hit attentions. Sparse attention to be is what I denoted on the hidden dimensions, hidden dimension and number of hits, right? And so this basically gives me the block here. There are a few more things that I need to initialize. For the normalization here, we are going to use batch norm. So I need 2 batch norm, and I also need a feed forward network, which is 2 linear layers. So batch norm 1, batch norm 1D here, BN2, the same. And for the feed forward, well, amazingly that collab suggests me most of the things. So here we want to change the in-between dimension a little by multiplying it multiplying the hidden dimension by 2. And we use linear tree-loop activation. Next, we will flow the informations to get the output. So forward functions take input as adjacency matrix A, and the hidden representation of the data point H. A here has size n by n, and H has size n times hidden dimensions. Well, first we will compute the output of the attention block. So H1 is what we get at this point. And next step, we need to add residual connections and normalize it. So H now will be normalizations too fast of the addition of H and H1. I can say this is the first addition and normalizations. So now we are here. We will feed the input, the output that we obtain through this FFN. H2 equal to self dot FFN H, and then we apply the second FN norm. H self best norm H plus H2, and we get H. All right, so this is one single graph transformer layer. The next step is to stack multiple these graph transformer layer in order to get our model. Well, so here is basically the structure of the model that we will be implementing. We have the input that are processed, that are fed through the graph transformer layers. For the task at hand, we are going to do a graph classifier, and for graph classifier, we will put some pooling layer on top. That is simply a layer that aggregate node features of the graph, and after that we implement. After that, we add a classifier layer. A classifier layer is simply combine multiple linear layers. So in this case, the input that we have is the graph, the node features of the graph, and the positional encodings. I haven't talked about the positional encoding. Let's just assume we have this as input. The shape of the positional encoding will be n by k, where k is hyperparameters. First, we will pass the original data into hidden representations, into hidden dim, which will be passed to the model. So we project the nodes into hidden dimensions to get the hidden representation. And then we add positional encoding to the hidden representation. So this is exactly what we get here. After that, we will feed this through a stack of graph transformer layers. All right, so let's start by coding this graph transformer model class GT model. Okay, I want to set positional encoding dimensions. We can set any value for the time being. We will correct it later. I want to have 8 layers, and 8 heads. The dimension is 80. First, we will project the original graph features, sorry, node feature X into hidden representation. And for this, I'm going to use item encoder to encode the original graph features. Project X into hidden. So X here denote the original graph features. Item encoder into hidden dimensions. I also need to project or change the dimension of positional encoding to hidden dimensions so that I can add the positional encoding and the hidden dimensions. Okay, no, this is not what I want. It should be linear from positional encoding dimension to hidden dimensions. This is positional encoding, map positional encoding to hidden dimension. And next I need to stack multiple stacks graph transformer layers. So self layer will be a modulus where we have in this modulus graph transformer layer hidden dim num hits. Well, for the index here runs number of layer times. Okay. Yeah, in range. And lastly, after all the graph transformer layers, we need the pooling layer on top so we can aggregate the node features. For this, I will use some pooling. From the DGL library and classifier layer on top here, self classifier. So we have a stack of linear layer followed by ReLU. And next one will be linear. Oh, interestingly, this is almost what I want, except for the last one. It should be the number of class for our classification problem, which I denote as out size. Now this should be also a parameter for our module. Alright, so now let's define the forward function. The forward function take input as the graph, its node features, and the positional encoding. Well, so first we will stack the, we will get the indices of the edge of the graph. In order to do this, we stack the endpoint of the edge. So g.edge here give us two lists, one list of start point of the edge and one list of the endpoints. We stack them together to get pairs of indices. We also need number of nodes. Well, here note that because we have G, so we don't need, we need to create the adjacency matrix ourselves, and adjacency matrix can be created based on the indices. So this is a sparse matrix. You see the suggestion here is correct. Yeah, so we can create the adjacency matrix, and now we will prepare the input by adding the hidden representations H with the positional encoding. So H now will be okay. So we map X into the hidden dimensions, and we add with the positional encoding. Positional encoding. Okay. Now we get the input that is to be fed, that is fed through these structures. For layer in self dot layers, H is equal to layer AH, and on top here, well, it's amazing, right? Puller to aggregate the features, and finally we have classifiers. All right, let's run it. Now we have the model. We are ready to train it with a data set. For the dataset part, I will not code it live, so I will just put in my dataset and run through it. So the dataset in this case is a OGBG MOLHIV dataset. It is, so let me run it to, why there is some, must be some import that was not properly imported. Okay, this was not reload properly. I don't need this anymore, so that makes the screen bigger. Basically, this dataset is a collection of graphs which are labeled with 0 and 1, and we are doing a classification task here. And here is just some exploration for the data. And in this block of codes, I split the data into chain validation and test with batch size equal to 256. And here is Laplacian positional encoding. You might have been familiar with the positional encoding in the transformer, where we use the sine and cosine functions. For Laplacian positional encoding, what we do is we we use the k lowest eigenvectors of the data features, and we encode them, we use them as the positional encoding of the features. And this Laplacian positional encoding is in fact generalizations of the sine and the cosine method that were used in transformer. So here you can see the dimension that is chosen here is twice of the dimension of the data, of the original data. And what we do in this case is we factorize we use eigenvalue decompositions of the original data, and we choose the k lowest eigenvectors, k eigenvectors that correspond to the k lowest eigenvalues. Okay, so it's loaded now, and here you can see we have two labels, 0 and 1. Here I extract out the first graph. There are 19 nodes in the first graph, 40H, and this first graph is label 0. Here I print out the statistics of the chain loader. Chain loader here has 32,000 graph, 129 batch. The batch size is 256. For the first batch, we have number of nodes, and we also have, I also print out some labels for the graph in the first batch. We do some Laplacian positional encoding. This will take some time. Right, so now we will train our data using the model that we created. First is the chain loop. So we need a data loader or loader loss function device. Set total loss to zeros. Put the model to train for batch and labels in loader. First, we put them to the correct device. Well, the output in this case is logits. We take in the input as batch here means the graph, and we take in the features of the graph, which can be extracted by fit, and also the positional encoding, which we created above, that is PE. Loss here will be computed between the logits and the labels, but note that the label right now they are in integers, so we need to convert them to float. Optimizer 0 grad, loss backward optimizer step, and then we update the total loss, right? And for this function, we will return total loss, but here we need to divide by the number of batches. That is the train loop, and next will be the evaluation loop. We put the model to evaluation mode, y2 and y regions. First, we initialize them as empty list. For batch labels in loaders, label device, we convert them to the correct device. We don't need this. Now our y2, we will append the labels. Well, we want them to be in the correct shape. Detach and put to CPU. While prepped, we will append our predictions. Y head dot detach. Okay, so here I should have computed y head, which is the model output. So graph features and positional encoding. So after this, we will concatenate them. Y2 cat along the first dimensions, put to numpy. Okay. Well, and we will create an input dictionary which will be used to compute to be evaluated for the evaluations. I should have mentioned that in this case we have binary classification problems, and the metric that we use for binary classification problem in this case will be the ROC AUC. So basically this metric is more efficient than the usual accuracy, because not only it gives us information about the percentage of correct prediction, it also gives us information about the percentage of the false predictions. And here I have evaluators, which is let me see if I have imported it somewhere. So evaluator here is API for evaluating the ROC AUC. So in this case, I initiate this API for our dataset. So it is a global parameter. All right. Okay, so it looks like we are all set. And to make the training looks neat, let me combine the chain and the evaluation into one function. I need copy because I want to save the best model. Model, I need chain loader, variation loader, test loader, number of epoch, loss function, well, device, okay, number of epoch is already here, and optimizers. Well, I should have optimizer in my chain function as well. Okay, so now let's do train and test on this single functions. First, initiate the best model to none. Best okay, validation, accuracy, I should say ROC equal to 0 for epoch in range num epoch. We compute train. So here we use chain loaders. Train result will be evaluation. Yeah. We run it. The validation result will be the model evaluated on the validation loader, and then test result will be the model evaluated on the test loader. From here now we will extract the value of for the ROC, AUC for chain result, validation result, and test result. Chain result IC, ROC, AUC. Well, collab is amazing. And then we have test. Alright, so now we would like to save the model. If the validation result is better than the current best validation result. Wow, amazing. And let's print out some statistics. Epoch. Chain loss. Wow, this is unbelievable. Let me put another line here. I think I should use single quote everywhere. Why is there? All right, no more mistakes. And here I would like to return the best model. Now we are ready to train the model. Here is a usual training routine. To save time, I have already written it out. We set the device to be CUDA. If you train by CPU, I think it will take forever to train. We create the model. We will train for 10 epochs. The loss that we use is binary cross entropy with logit loss. This is more stable than the plain binary cross entropy applied on sigmoid. So this loss is applied where the output is logit. Optimizer will be the idiom optimizers, and then we run the train and test function, save the best model, and after 10 epochs, this is our result. Let's say now you want to evaluate the best model, which means the model that performs the best on validation test on test set. Then you simply evaluate this model on the test loader and then print out the result. Right? So result for the best model on test set is 0.70. If we look here, then it should be this one. This one has validation score 0.78, which is highest among all the scores, so it should be the best model. And that wrap up this tutorial. Thank you for your attention. If you find my tutorial useful, please subscribe and give me a like. Thank you. Bye.